Thank you very much, Judy, for this warm introduction and for pronouncing all the Greek names right. That was very impressive. And thank you to the Radcliffe Institute for giving me the opportunity to be here this year. And thank you to all the fellows that make this year actually a remarkable intellectual endeavor. I have really, really enjoyed the first couple of months. I also enjoyed a lot the various talks that I attended here that other fellows gave. And I must say that listening to all these talks, I got very stressed preparing mine. One of them because they were superb. The second thing is because this is not really a public talk, right? If it was just a public talk, I would just show nice pictures and movies and telescopes and everybody will be happy. It is not a professional talk because then I would show things that I really do, which look like this. And, oops, there we go, wrong direction. And this is equation number 56, mind you. And yet, what I consider this audience to be is a group of highly intelligent and educated intellectuals that not only want to know what we're doing, but also want to understand why we're doing it and what was the process that let us make the decisions that we're making. So what I decided to do is that the second part of the talk, I will focus on this wonderful, how do you call it, arrogant experiment that will allow us to take the first ever picture of an astrophysical black hole and allow us to test Einstein's theory of gravity. But I will start the beginning of the talk, the first part of the talk, effectively giving you a history of how those ideas were developed, because I want to make 2 points. One is that some of these ideas are truly revolutionary, and the second thing is that in order to make truly revolutionary ideas in science, you only have to make small but very bold steps that you cannot do without. And this is the kind of points that I will try to make. So let's start at the very beginning, a very good place to start, whatever it's called. And Einstein did most of his important work in the beginning of the 20th century, so it's important to discuss what was the landscape of physics at the end of the Victorian age, the end of the 19th century. And it's fair to say that most physicists preoccupied themselves with 2 general ideas. One is thermodynamics, which is the physics of heat and engines, and the other is electricity and magnetism, which is the physics of cables, electricity, magnetism, and light. And this was a wonderful time to be a physicist, just like today, because people could actually see immediate applications of those fundamental theories that changed remarkably, brought the industrial age, transportation, quality of light, Edison and the light bulb, and telecommunications, just like today. And people became more and more arrogant by realizing how that works. And the end of the Victorian age in physics is actually marked by this very famous speech by Lord Kelvin. And you might have heard the name Kelvin by the Kelvin degrees in temperature scale. His name was actually William Thomson, and he was the first Baron of Kelvin. He gave this talk in April 1900s, and he talked about the status of physics at the end of the 19th century. He called his talk 19th Century Clouds over the Dynamical Theory of Heat and Light. And he starts by saying that the beauty and clearness of the dynamical theory is at present obscured by 2 clouds. What he really means to say is that we understand all the physical experiments that we do. We have 2 theories that can tell us absolutely everything, but there are 2 little problems. And that ended up being a very short-sighted remark, because it turns out that one of those little clouds was the beginning of special and general relativity. The other was the beginning of quantum mechanics, which is, of course, the scientific revolution of the 20th century. But let's give that to him. And I'm not going to talk at all about the quantum mechanics aspect. I'm going to talk about, starting from this point, why one of those clouds led Einstein to his new theories and to black holes. And that cloud I would like to call the relativity of speed. This is the very intuitive concept that what you assign as speed to something that is moving depends on how fast you're moving yourself. Right? This is something that comes from common experience, and the easiest way to demonstrate that is I can be sitting on the top of a mountain in Chile looking at the sky and the telescopes, and then I can take a time-lapse movie. Of course, time is moving much faster than it really does. You can see the stars and the galaxy coming around and moving from east to west. Now, we don't really believe that the stars are moving from east to west. What's happening is that we ourselves are taking part in the motion of the Earth, which is the other way around, and we attribute this motion as a speed for the stars, like it seems as if the stars are moving. So what you yourself defined as motion from somebody else depends on how much you're moving yourself. That was fine, and all the way until the beginning of the 20th century, pretty much all phenomena in physics seem to obey that rule. What you measure as speed depends on how fast you're moving, with one little cloud, one little exception. And that little cloud was light. There was both experimental evidence, and for those of you who understand what that is, I'm not going to say anything, and there was theoretical interpretations of those experiments by another famous physicist, James Clerk Maxwell, that demonstrated that when you look at light and you try to measure its speed, it doesn't matter who is measuring the speed. It doesn't matter how fast you yourself are moving. You always get the exact same speed. And if you spend a second to think about it, this is extremely ridiculous, right? It's like I'm driving Garden Street is that way. I'm driving up Garden Street towards the hill, and I look outside, and I look at the clouds, and I measure the speed with which they're moving backwards towards the square, right? I'm happy. I turn around, I start driving with the same speed towards the square, I look out the window, and guess what? The trees are moving with the same speed with me towards the square. Right? That's what it means that I infer the same speed of an external object, no matter which way I'm moving. That clearly is counterintuitive. And this is something that bothered scientists for a very, very, very long time, several decades, because nobody could come up with a way to look at science, to look at the experimental results and make sense out of it. And this is where Einstein came. In 1905, what we call the Year of Miracles, because he wrote a number of articles that actually changed fundamentally the course of physics, Einstein introduced his special theory of relativity to remove that paradox. A side product of that theory is his famous equation. Here is from his manuscript, E equals mc squared, plus other terms that people usually don't think about. But I'm not going to talk about this particular aspect. We're talking about the relativity of speed here. And what he said is the following. What is really speed? Speed involves space and time, right? If I move 100 miles in an hour, my speed is 100 miles per hour. Now, I want somehow, as I move as fast as light, the measurement of speed and measurement of time to conspire in such a way that when I take the ratio, I get the exact same number, no matter how fast I move. Right? That's the only thing that's the only way to explain the problem. And what does that mean? It means the measurement of time and the measurement of distance depends on the speed of the observer. So suddenly he took the relativity out of speed and he turned it into the relativity of space and time. And that's why he calls it the special theory of relativity. Now, that's a little bit of a misnomer, because when we think about theory of relativity in a, not thinking too hard, we think that Einstein said that everything is relative. Actually, Einstein did exactly the opposite, right? He said space and time are relative, but there's something absolute, the speed of light, where I wrote it. The speed of light is fixed. And more properly, the theory should have been called Einstein's theory of the absolute, as opposed to Einstein's theory of relativity. That would have been a lot more appropriate. And it turns out that it's impossible to make a physical theory where everything is relative. You always have to have an anchor on which you base things. And this is the anchor that he used to make his theory of special relativity. Okay, nothing so far so complicated. But then Einstein realized that, this is a little weird, because if everybody measures a different space and a different time, how can we ever agree on what is the result of an experiment, right? If I ask you and you give me a result and I ask you and you give me a different measurement, how can we ever compare? So he actually became very obsessed, and you can see it in his writings, making what became famous afterwards, a set of thought experiments, Gedanken experiments, where he would play out many, many different possibilities where he could come up with a paradox in his ideas. And these are very famous thought experiments because it turns out that there's no paradox. You can always come up with a very unique way of communicating people and comparing results and discussing how your relative difference in time and space. And the big part of it is how do you incorporate synchronization of clocks, right? If we have two clocks and our clocks are moving at different speed, at what point do we share information and tell each other what is the time? So this was the whole idea of his thought experiments. And when I was reading that stuff back when I was an undergraduate student, I was always impressed that Einstein was so obsessed with time. I mean, everything was about time and synchronization of clocks in his writings. And apparently I was not the only one. Peter Gallison, who is a professor here at Harvard, wrote a beautiful article in 2000, many years after I was a graduate student, and I read it soon afterwards, where he said he had the same mission. He was sitting in in none of, maybe it was Zurich, none of the stations in Switzerland. Einstein was living in Switzerland at the time, and he was surprised that Einstein was so impressed about time and synchronization, and then he looked up, and you know what you look up when you are in Switzerland? You just look at clocks that all move at exactly the same time. And this is actually from his article. This is a diagram of the city of Bern. Actually, that's where Einstein lived, and all these red circles are clocks on the city that are connected with an underground electric circuit to make sure that they all show the exact same time, right? So it is actually not that surprising that Einstein was obsessed with clocks and synchronization, because he grew up, he woke up with them, he went to work with them, he went to sleep with them, and it was always part of his life, which I think is an interesting side about Einstein and his theory. So, okay, Einstein resolved one of the clouds of the 19th century, but very soon he realized that he actually introduced an even worse cloud. And that is the fact that there is something that was not working with his ideas, and that was gravity. Why was that a problem? Because his whole point of making the speed of light constant required in his whole framework that nothing moves faster than the speed of light. This is one of the basic principles of physics that we believe in today. But there was something that does move faster than the speed of light, and I would call it the speed of gravity, and I will explain in a second what that means. Remember what gravity is, right? We have the Earth, we have the Sun, and Newton told us that the Earth and the Sun feel a gravitational interaction, and one goes around the other. But the Sun is not fixed, it's not staying constant, it's moving in the galaxy. So somehow, the Sun, with its gravitational force, communicates that information to the Earth, and the Earth is coming around with it, right? The Earth is not left behind from the Sun in the motion in the galaxy. And Newton told us that this is done instantaneously. When the Sun moves a little bit, the Earth knows immediately and moves together with that. But that was impossible in Einstein's new world theory. Nothing could be communicated instantaneously. So he spent 11 years between 1905 and 1916 working, very frustrated, working with serious problems. It was during the last 2 years during the First World War, and at the time he had moved to Berlin, trying to make a theory of gravity that had this finite speed of propagation. And he just couldn't. And we know now why, because it is impossible. It is impossible to make a theory of gravity that agrees with all the experimental data and yet to have a finite speed of propagation. And that was a big problem, and Einstein solved it in a very Einstein way, and I will explain that in a second. He said, to hell with gravity. Right? These are the small, bold steps that you need to make scientific revolutions. He effectively said it doesn't exist, right? There's no such thing as gravity. You're going to say here, okay, hold on a second. The whole point of science is, experiments in the world, and you look out, make sure that everything agrees, and I can make a trivial experiment, right? I can take my keys, and I can let them go. Why did it go down if there's no such thing as gravity? And of course, this was Einstein, so he had a few of those wonderful thought experiments, and he said, this is just an illusion. And let me explain what do I mean by an illusion. He said, let's think about it through, okay? Let's assume that, forget the Earth and the atmosphere and all the other potential forces. Let's take 2 stars, put them far away from everywhere, and let them go. Now, you would think that if there's no such thing as gravity, the only thing that would happen is that they would go down straight lines, right? Because nothing is there to perturb their motion. And yet, what really happens is one attracts the other, and they eventually crash to each other. So you and I would have looked at that and interpreted that the straight lines would have gone up and down, but the paths of the objects are actually curved. What Einstein said is that, no, these are straight lines, and these are curved lines, and the paths of the objects are actually straight. And it's just an illusion. But if they were indeed straight and parallel, how is it possible that parallel lines cross? Right? The whole definition of parallel lines from the ancient Greeks is that you send down through 2 parallel lines, like a railway, right? And they never cross. Is there any way to have 2 parallel lines, illusions or no illusions, and eventually cross? And Einstein was very fortunate because it actually is true. That is possible. And with his friend Marcel Grossman, that was back in Switzerland, they actually started reading the ideas of a famous mathematician who died extremely young, Bernard Riemann, who wrote an entire thesis in the mid-1800s called on the hypothesis which underlied geometry. And Mr. Riemann asked the simple question, is there any way to make two parallel lines cross? Now, it doesn't get more abstract than that, right? He didn't have much luck explaining that in cocktail parties and stuff, but it ended up being extremely, extremely useful for relativity. And it's actually very easy to see why. I'm going to make a little demonstration here. How is it possible to make two parallel lines cross? So here's a blow-up of the map of the Earth. You can recognize the top part of the North America. This is the equator. This is the country of Ecuador. And what I can do is I can take two straight parallel lines coming out of the equator. How do I know they're parallel? Because they're both perpendicular to the equator, right? This is the definition, if you want, of a parallel line. They look nice and parallel. They don't cross. But then if I zoom out, they do cross, right? They do cross at the pole. All the lines that start parallel in the equator do cross at the pole of the Earth and the other side as well. And what that demonstrates, which is actually the whole idea of Riemann's geometry, is that the fact that parallel lines do not cross is true for flat space. Right? If you draw two parallel lines down there, they will not cross, assuming that this continues to be flat. But the minute the space, or space-time if you wish, gets curved, then things that start as parallel lines eventually cross. And this was the remarkable intuition that Einstein had, that what gravity really is not a force and interaction between particles, but the minute you put a massive object in the middle of space, that massive object curves space-time, it warps space-time, such that the future of all the other objects turn towards that big massive object. So the reason that gravity works is not because things interact with each other, but because they turn their futures towards each other. This was the fundamental intuition that Einstein had. Now, you're going to say we had a little bit of discussion of parallel ways of interpreting the same reality. Is that any better than Newtonian gravity, other than the fact that you can make it have a finite propagation speed? And there was an obvious interpretation. If it is parallel lines that appear bent, then anything that follows parallel lines is going to appear attracted by gravitational objects, by anything else. And light, for example, that light always goes along straight lines, will also appear as it gets attracted by massive objects. Newton did not say anything about light, will not even care about massive objects. Right? Light has nothing to do with gravity, but Einstein said no, light follows straight lines and all straight lines are curved. So in this particular demonstration, if you put the sun in the middle of space-time and you make it curve, and you put a star behind it, then the light from the star gets bent as it goes next to the sun. And since we don't know that this is happening, we assume, this is our interpretation, that the location of the star has actually moved. So the central object acts like a gravitational lens because it lenses the light to move it in a different way. That was a prediction that was written in the original paper by Einstein in 1916. And very quickly, within 3 years, and the only reason it took 3 years is because people were waiting for the First World War to be over, English astronomers, British astronomers, went out to a place where they could have a solar eclipse, because, of course, if you want to see stars during the day behind the sun, you need to have the sun blocked. This is the negative from one of those pictures. This is the moon. This is the solar corona. And those circles, you can probably not see them, shows the location of the 4 stars that they measured, their position. They compared that with the position 6 months earlier when the sun was in a very different place, and they show a displacement. Not only that, the displacement was exactly what Einstein predicted in his theory, given the mass of the sun. And that was remarkable news. Suddenly, we start talking about curved space-times. We're talking about space-times to begin with, and Einstein becomes very famous. And even New York Times reported the wonderful discovery, lights all askew in the heavens, very New York Times title. Stars not where they seemed or were calculated to be, but nobody need worry, whatever. A book for 12 wise men. And no more in all the world could comprehend it, said Einstein when his daring publisher accepted it. Of course, this is all bogus. None of that ever happened. He published it. He gave a talk, and he published it in the Proceedings of the Prussian Academy of Sciences. But, it made a better story. It's the New York Times. But the punchline is that this is, of course, what made Einstein, a worldwide icon. And you can see his face in pretty much all candidates have one way or another of demonstrating how much they appreciate what he has done. And this is what I usually to talk about Einstein being an international icon, but Halloween 2 days ago, I was actually walking around and I saw a crazy scientist dressed up with like white hair going like that, and everybody said, "You're a crazy scientist." And, Einstein is a household name and a household appearance. So this was where all his ideas came from. And you see there are small steps trying to solve one problem at a time, and you're getting deeper and deeper and deeper down the drain, literally, by making more and more bold moves to make everything work. But fundamentally, then you look at experiments, and the experiments either confirm you or contradict you. And for the case of Einstein, they confirmed it. But then, very quickly, actually 2 years after the discovery of the development of general relativity, people started realizing that you can even take that theory to a higher extreme and say, what if I take a star and I crunch it so much, I make it so small and dense, that when light from the star comes out, it gets bent so quickly that it turns back into the star. So not even light can escape, right? And this is the whole idea of a black hole, an object so collapsed, so dense, so gravitationally strong, that it does not even let light escape from it. And now I'm going forward 80 years, because there was an incredible amount of work, both theoretical and experimental, people really arguing and fighting this notion, because it seems extremely counterintuitive. Do black holes exist? Do black holes get formed? How would we know if we see a black hole? But with the advent of modern telescopes and modern technology, there has been multiple ways of finding circumstantial evidence that black holes do really exist in the universe. And in my mind, by far the best one, until very recently, was the black hole in the center of our own galaxy. And how do we know that such an object exists? When you take a picture with a very large telescope, this is from the Keck telescope in Hawaii, in a particular wavelength, all the way at the center of the galaxy, you see a number of stars. And don't worry about the colors, because those colors are meant to demonstrate something else. And if you take the picture in 1995, and then one picture every now and then what you see is that all the stars, all the way to 2007, 8, 9, 10, and so on, all the stars orbit a very common center that, of course, has an asterisk here, but there's nothing there, no light comes out of there. This is just to demonstrate what that common center is. And you can do the usual physical exercise that an undergraduate student can do and infer how big is the mass of that object in the center that attracts all of them, that makes them orbit. And it turns out to be equal to 4 million times the mass of our sun. Now, you have an object here that is 4 million times the mass of the sun, and yet it's not as luminous, not as bright than any of those single stars, right? You want to confine 4 million stars in a place and make them not produce any light. And it turns out that the only object that we know astrophysically or physically, or we can envision that could do that, is a black hole, nothing else. So this has been, until very recently, the discovery of gravitational waves, which I'm not going to talk about, the best evidence that there is something very massive and very black, a black hole, in the center of our galaxy. So what we wanted to do is, like the Thomas from the Bible, is we wanted to see it to believe it. So several of us decided that we really want to take a picture of that, an actual real picture of that empty space in the middle of the galaxy, and see, is it really a black hole? And of course, the question that you're asking is how big that hole is meant to be, what it will be like taking a picture of a black hole. And I can give you numbers, but they're so small that I cannot even understand what these numbers really mean. And the similarity that I can make is I can say it's like equivalent of taking a picture of a donut. So this is a hole and there's stuff around it. Like this is what, to 0th order, we expect the black hole to look like. However, that donut is going to be extremely small because it's really far away. It's at the center of the galaxy. And how small it would be? It will be like taking a picture of that donut on the surface of the moon, right? This is how small it's going to look. Now, I'm sure you've all seen pictures of the moon, and I don't think you've seen anything as small as a donut in any of them. No current camera, no current telescope has a resolution like that. And therefore, you had to think way out of the box of how to make that happen. Keep that thought. The second thing is, what does it really mean to take a picture of a black hole? right? What is a hole? What would a hole look like on an empty sky, on a black sky? It will look like nothing. You wouldn't be able to see anything. But the galaxy is never really black. There's always clouds, there's always plasma, there's always hot matter that is orbiting around. And all those stars that orbit the black hole spew out a lot of that hot matter. So if you look at the right part in the electromagnetic spectrum, you might be able to see the silhouette, you might be able to see the shadow, the hole in the bright background of the diffuse emission. And when I was talking before about how would it look like, of course, nobody had any intuition, but I think a lot of you might have an intuition of how a black hole would look like. For those, I guess this is not the right crowd for this joke. So Interstellar is a movie. Movies are things that you go and watch. If we have a few of the movie directors in this audience. But there was a movie that became pretty well-known in the sci-fi genre, I guess, a couple of years ago. It's called Interstellar, with a couple of famous actors. And what they did is eventually they go into a black hole, and this is what the black hole is supposed to look in their case. There's a lot of plasma material around and the shadow of the black hole in the middle. Now, for some reason, they wanted to make it very realistic, and they asked one of the actually fathers of black hole astrophysics, his name is Kip Thorne from Caltech, to help them out to write all the various equations and do the real calculation with Einstein gravity and lensing and everything of how black hole looks like. I don't know why, because when I go to the movies, I don't care how realistic it looks like. Right? When I go to Harry Potter, I'm not asking why a hippogriff works. Right? Maybe Michelle likes those things. I know she gave a talk about that the other day. But what was interesting, what I found very fascinating related to our work, is this quote from a Wired magazine discussion about the movie Interstellar, where they say that some individual frames took up to 100 hours to render, the computation overtaxed by the bendy bits of distortion caused by an Einsteinian effect called gravitational lensing. Each one of those frames in the movie, and this is high frame rate, took them more than 100 hours to render with the correct physics. And that has actually been a problem that we've been dealing with. Because we want to know what would the black hole look like in order to train our telescopes to look at them. And we were always confined by the fact that computers were not fast enough. Because what you want is you want to send millions and millions and millions of light rays into a simulation, just like a weather simulation, what happens around the black hole, and turn it into an image. And that was extremely computationally complicated. So something that we did, and that made a very, very big difference at the University of Arizona in our group, is we realized that each one of our computers, and even each one of our cell phones, actually has a specialized microchip that allows you to do very, very quickly rendering of images. It's called the graphics processing card, the graphics card. And because of computer gaming, they have actually been developed so quickly that if you care to do nothing else other than rendering, they can do it remarkably fast. So what we did is that we hacked into it, and we added a black hole, why not? And this is the hand of our postdoc who actually did most of that work. And we let the graphics card of the computer do the rendering. So we provided the information and had the graphics chip of the computer to do it. And our computer algorithms became so fast that now we don't show animations that come out of our simulations. We actually show ourselves running in real time the simulations. And not only that, but they're so fast that Chiquan, who does that, cannot type fast enough commands in order to make them, to stop it, start it, and everything else. So he has a little interface here. It's called a leap pad. It's like the Xbox, that he can actually control the simulation with his hands, like Minority Report style, right? And so you will see what will happen. This is the black hole. It's on YouTube as well with some cheesy movie music if you want to see it. So this is the black hole, and he's going to throw a wall of 1,000 light rays. And as they go close to the black hole, they're going to get scattered away, and he's going to stop it, explore it, do various things that he wants to do. So there he is. This motion says start the simulation. There's the one, million light rays. He stopped it. He can turn it around all real time as the calculation is happening. He can zoom it in. These are all the light that this is the black hole. It's about to cross into the black hole. It turns very red, gets scattered, gets a particular structure, and he can move it all around. He can go forward in time. He can go backward in time. This is the kind of ways that we're using these particular interfaces and the extreme rapid algorithms that we developed to understand what happens to light close to a black hole and make appropriate predictions. Now, I think this goes on first. He has forward in time, backward in time. Yeah, it's mesmerizing, isn't it? Yeah, imagine doing it yourself. So sometimes I come and do it here in front, but I usually fail because, while you're talking, you're showing and it doesn't really work. So I just saw the YouTube videos a little better. And the joke that we actually had a little press release about Interstellar when it came out, is that it's great with that movie, but we can literally do it faster just by waving our hands. Right? Yeah. Okay. Waving your hands in science means that without putting any effort, right? In any case, a science internal joke. So, of course, we didn't want to just use our laptops, because if we can do it so fast in a laptop, imagine if you actually built thousands of those graphics cards and make a supercomputer out of those graphics cards. So we built a special purpose supercomputer just for that project. And this is people putting it together at the University of Arizona. And when we put it together, we actually became number 7 in the fastest supercomputing per wattage of power used in the world, which we were very, very impressive. No other institution other than Cambridge University, and definitely no other institution in the United States, had at the time a supercomputer that was so fast. And we were very happy because now we can throw the plasma onto the black hole, we can throw the light onto the black hole, we can throw everything and the kitchen sink, and calculate a truly realistic simulation of what we think the black hole in the center of the Milky Way will look like. This is weather-like, this is turbulent, this is very variable, this is hydrodynamic, this is like full of clouds and everything else that you can imagine. You see also we change the orientation of the observer, so you see it moving up and down. You see primarily the motion of the swirling of the plasma as it goes around. You see the black hole shadow, which is right here in the middle. And you see those 2 big jets that the black hole sends because it is very rapidly rotating. And it gets some of the matter in and some of the matter it blows out. And these are the kind of simulations that we're looking at. It turns out that by looking very carefully at what that shape and the size of that shadow is, this is where we're doing all the tests of Einstein's theory, right? Because that shadow tells you what the gravitational field around the black hole is, and by doing all these measurements, we can see whether Einstein was really 100% right or not. But one of the reasons that we did all of those numerical experiments is because we wanted to know what is the optimal place in the electromagnetic spectrum to look at. Because it's not enough to have a big telescope, and I haven't told you anything about telescopes, we're doing theory here. It's not enough to see what the black hole will look like, you also need to look at the right place. And there's a number of coincidences that need to happen, if you wish. The atmosphere needs to be transparent, and the atmosphere is not transparent in all parts of the electromagnetic spectrum, otherwise the X-rays from the sun will have completely evaporated us a long, long time ago. The galaxy needs to be transparent all the way to the center, and again, that puts a lot of constraints. And the plasma around the black hole needs to be very transparent. And if you look at slightly different part of the electromagnetic spectrum, and this is, for example, at 3 centimeters wavelength, then you wouldn't see the shadow of the black hole that I showed you before, but you see this fog of plasma around it. And this is a result of our simulation, but this turns out to be the very first project that I did as a postdoctoral fellow here at Harvard when I came in 1997. This is a very dear project to my heart. One reason because I love black hole astrophysics. The other reason is because I did it together with a graduate student at the time who ended up being my future wife. So this is a very wonderful project. And she's actually right now giving a similar talk at the University of Chicago, across the country. But this is what you would have gotten if you made the observation at 3 centimeters. But if you look at a different part of the electromagnetic spectrum, what you see is that the fog becomes more and more and more and more transparent. And if you pick the wavelength of the observation right, you will see the black hole shadow popping out. So the reason that we did all those computational numerical models is to actually identify what is the optimal place to look at that shadow. But again, theory, right? In theory, everything is fine. In practice, it isn't. And what made the next big technological leap, the next big transition, is the demonstration in 2008 using only 3 telescopes, 1 in Hawaii, 1 in California, and 1 outside of Tucson, combined together as a big telescope the size of this entire triangle. by a number of people led by Seb Dolleman, who is the PI of the project right now, who turned those 3 telescopes to the black hole in the center of the galaxy. They couldn't, it was small enough, it was only 3 telescopes very close together. They could not take an image, but they could measure the size. And they demonstrated that the size is comparable to the shadow, to the black hole shadow, and everything in between is transparent. And that has been a remarkable demonstration that all these ideas, all those theories, everything that we all talked about is actually something that has the possibility of working. Was I right? Not will work, has the possibility of working. So a number of people got together at MIT Haystack Observatory in 2010. Sep, in the meantime, moved to Harvard. He is now at Harvard Observatory. But of course, the more people got excited, the more and more people joined the collaboration. So, when something becomes hot, everybody likes to be part of it. So we hosted the inaugural meeting in Tucson in 2012, nice, beautiful weather. Next one was in November 2015 in Canada, horrible snow. The 3rd meeting is actually the week after Thanksgiving here in Cambridge, Massachusetts, down the river someplace where we're all getting ready for that experiment. Now, of course, as the group of people becomes bigger and bigger, and these are people from all universities all around the country, I found that it has been extremely complicated and remarkable to get different people from different backgrounds, ethnic backgrounds, social backgrounds, and everything else, agreeing on how to do a single experiment. And to quote my wife, I would say that I don't mind with dealing with the complex mathematics of the universe. It's people that I don't get. And if you actually work on the sociology of science, please come and study us and tell me what the answer is at the end. But somehow we managed to make this whole thing work. Now, the reason that, of course, it took some time since 2008 is because they used only 3 telescopes. We're not building new telescopes because these are extremely expensive processes and nobody has the money. But people go to every single radio telescope that exists around the globe and outfitted with the proper equipment to do that observation in the proper wavelength. And this is one of our colleagues, Dan Maron, his finger, pointing out a radio receiver. Everything is gold-plated. Everything is highly calibrated, highly put together. You build it at the basement of a university. Then you transport it to the telescope. This is the Large Millimeter Telescope at a volcano in Mexico. And this is Seb Dolleman, the PI of the project, inserting something in one of the mirrors in the telescope, trying to get it ready. This is from the New York Times. Some of the telescopes are easier to reach than others. Judy talked about the ALMA in Chile, which is almost at the base camp level of Everest. It turns out that there's one that is even more difficult to reach, and that is the South Pole Telescope, which is actually at the very center of Antarctica. It's a wonderful place to do observations if you can make it there. And this is our colleague Dan Maron, who shows that he is really good with weather. He left his parka out. This is the South Pole. And this is the little instrument that he was building before, and that's his graduate student. And we were all joking that he didn't leave him there at the end of the day. So what happened in the last 8 years is a remarkable convergence of about 150 people all around the world to build all the telescopes that are required, all the instruments that are required, literally transferring them by hand and install them in every single telescope that is required. And that's how we got together the Event Horizon Telescope, which has telescopes anywhere from Hawaii, those 2, Northern California, Tucson, Arizona, Mexico, ALMA in Chile, the South Pole Telescope, which is down here, APEX, which is also in Chile, and 2 telescopes in the French Alps and in the Pyrenees. And all of those telescopes are, as we speak, completely outfitted, ready to turn. And the only thing that they're waiting for is for the galactic center to come from the backside of the sun. Because right now, the galactic center is the place, it's behind the sun, and you cannot see it. And that will happen this coming April. So we're at the point where everything is ready. We're all keeping our fingers crossed. We're hoping that very soon this is a simulated image that will come out of the Event Horizon Telescope, given the best that we know about how the instruments are going to work and how the weather is going to work. We're keeping our fingers crossed, and we're hoping that very soon this won't be a result of simulation, but this will be a real first picture of a black hole in the center of the galaxy. Thank you very much.